Hello everyone, hope you all are doing good. I am Anjana from Learnohub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 9 Physics Chapter 8, Propagation of Sound in a Medium. We will be discussing the production and propagation of sound. Also solve questions from exercise 8a. Are you all ready for the session? Let's begin. So what is sound? When you see a housefly, so you all have seen houseflies, right? So you will be hearing some sound from there. Yes, when you have a mosquito around you, you will be resting somewhere or you will be sleeping. At that time, you will be hearing something. What is it? It is the sound of the mosquitoes. Then what you will do? You will try to kill the mosquito because it's very disturbing and you will try to kill the mosquito. You will hit the mosquito. When you hit, what is there? A sound is being produced. So in simple words, what is sound? Something that you are hearing is sound. Yes? Okay. What are the other instances? When I clap my hands, you can see some sound is being produced. Can you tell me other examples? For example, alarm. Morning, you wake up with the alarm. Okay. So you will be hearing some sound. Yes. Second, when you come to school. Okay. At school, you will be hearing the school bell. This is a sound. Then you will be hearing national anthem. This is a sound. Then sound from musical instruments. Sound from musical instrument. What are the other instances? When you drop a steel glass, okay, you are dropping a steel glass, you will be able to hear a sound. Dropping a steel glass. Then thunder. Okay, before rain you will be hearing thunder. This is a sound. What are the other examples? Vehicles. Okay, from vehicles, horn. Vehicle horn. Horn. Vehicle horn. Okay, so these are many instances where you will be hearing sound. So what is sound? You can define sound. Sound is a form of energy which gives us the sensation of hearing in our ears. In this case here, housefly is producing some sound and we are able to hear a sound. Okay. In case of alarm, the alarm clock is producing a sound, we are able to hear the sound. That is the sensation of hearing we have. School bell is producing sound, we are able to hear the sound. Okay. Then students will be singing the national anthem in the choir team. So they will be producing sound, we are hearing the sound. Then musical instruments are producing sound, we are hearing the sound. Dropping a steel glass. The steel glass, when it falls to the ground, it produces a sound, we are hearing the sound. Thunder. Okay. Thunder is being heard, we are hearing it. Okay. Horn from vehicles. It is producing sound, we are hearing sound. So you understood, it is in simple words, sound is nothing but it is a form of energy and it produces a sensation of hearing in our ears. Okay. How do we hear sound? You can see me talking. Yes, I am speaking from here and you are able to hear me. Yes. Why? Because I am the producer of the sound and you are the receiver of the sound. Here you can see a radio. Okay. Here a radio is there. A person is standing here. Okay. So he is able to hear. When the radio is on, it will start producing music. Okay. So this is a producer. Okay. Producer of sound we call the source. So there is a source. Okay, first thing, there is a source. Okay, how do we hear sound? To hear a sound, first thing that is required is a source, something that produces sound. Radio is producing sound. In the previous cases we have discussed housefly, mosquito, school bell, students who is singing the national anthem, then vehicle horn. They are producing the sound. So these are the sources. Okay, and a person is able to hear the sound. Okay, the sensation of hearing is produced in his ears. Yes, so this person is called the receiver. Receiver. So second thing is receiver. There is a source, there is a receiver. So you can see the sound starts from here and reaches here. Okay, so it is traveling. Sound is traveling. Through what? Sound is traveling. Okay, through a medium, sound is traveling. Okay, here what happens is the radio produces sound, that is it is producing some vibration, and these vibrations are traveling through a medium and the person is able to hear the sound. Okay, so three things that are required is, first, for a sound to be heard, there should be a source, there should be a receiver, and there should be a medium. In this case, radio is the source, the receiver is a person in whose ears the sensation of hearing is produced, and there is a medium, that is through air the sound is traveling. Okay, so what is sound? Okay, we know it is a source of energy. Okay, there should be a vibrating body, the source should be vibrating. Okay, this vibrating body will produce a sound. Okay, so the vibrating body causes vibration in the particles of the surrounding. So this radio, it produces vibration, this vibrations produce vibrations in the surrounding air. Okay, which travels in the form of waves with a certain speed. Okay, this we will be discussing. So these radiations, the radio is producing vibration, these vibrations are traveling as waves. Okay, and it will reach the person's here, there will be a sensation of hearing. Okay, his eardrum vibrates and he will be able to hear the sound. So we have said sound is produced by vibrations. Yes, so we will be discussing 5 different experiments. The first experiment, you can try this. Take a rubber band. Okay, place one end of the rubber band between your teeth. Okay, hold it tight with your teeth and the other end in your hand. Okay, so here you can see one end is in the person's mouth and the other end is held with his hand. Okay, other end is held with his hand. Tight it is held. Now what you have to do is plug the string, that is plug the rubber band with the other hand. Okay, one hand he is holding the end of rubber band, with the other hand just pluck it. What happens? Initially it will go down, that is the rubber band will stretch down, then it will move up, again it will stretch down, it will move up, it will stretch down, it will go up, it will stretch down, it will go up. This will be happening and finally it comes to rest. Okay, try this experiment. Have you ever tried this? Yes. So what you are able to hear? There is a sound that is produced. Okay, in this case a sound is produced. You can see that the rubber band is vibrating. It is moving down and up, which means it is producing vibrations. The vibrations become smaller and smaller. Then what happens? Finally it comes to rest. When it comes to rest, the sound will not be heard. Okay, so when it is vibrating, we are able to hear the sound. Okay, this is a rubber string which is vibrating by plucking with one hand. What happens? These vibrations produce sound. When it comes to rest, finally there won't be any sound produced. So this is your first experiment. Okay, second experiment, a vibrating wire produces sound. For this experiment, fix 2 nails, okay, and take a string wire is taken and it is held tightly between the nails. Okay, then what you have to do is you should take a small piece of paper and place this paper over the wire. Okay, in this way you can place the paper over the wire. Then you will start vibrating it, that is you will be plucking one hand. What happens? It starts vibrating. It will go down, it will come up, again go down, come up, it will be happening. So what happens is you will be able to see that this paper piece, okay, the paper rider you call it, it starts vibrating. Why? Because vibrations in the string will make the paper piece vibrate and finally it will fall down. Okay, so here you can see that the vibrating string is producing a sound. Yes, so when the string vibrates, it produces sound and finally when it comes to rest, it comes to stop, that is there won't be any sound. So you have seen many musical instruments, right? For example, a violin or a guitar. What happens? In those cases, a person will be plucking the wire or plucking the string. Okay, then what happens? It starts vibrating and these vibration, when it is plugged harder or when it is plugged in a lighter way, you can see different sounds are produced, and all these sounds are produced only because of the vibrations that are happening. These vibrations travel through the surrounding air and it will finally reach our ears. Okay, now in case of all these musical instruments with string, the same thing is happening. Veena, guitar, ukulele. In all these cases, the same thing is happening. Third experiment, a vibrating tuning fork produces sound. So what is a tuning fork? Tuning fork is a metal rod usually made up of steel or aluminium which is bent in the shape of a U. Okay, and there will be a metal stem. So this is how a tuning fork will look like. When you take a hammer and hit it, what happens is you will be able to see that it will start producing vibration. It will start vibrating and you will be able to hear a sound. Or just take a tuning fork and hit it on a bench or desk, something like that. Okay, hard object. What happens is it starts vibrating. You can feel the vibration. When you hold this tuning fork in your hands, you will be able to feel the vibration, how it is vibrating. Okay, and this vibrations is producing sound. In this experiment, what you are going to do is, you are taking a tuning fork. Okay, you can see this is a tuning fork. Then there is a tennis ball. Okay, then here you can see the ball is moving. How is the ball moving? First, you have to make the tuning fork vibrate. Okay, when it is hit on a hard object, okay, or when it is hit with a hammer, you can see that it will start vibrating and start producing sound. Now, when this tuning fork is just brought near the tennis ball, okay, you are not making, you can see the tennis ball is in this way, it is being hanged. Okay, so here it is not made to touch the tennis ball, but what is done? It is just brought near the tennis ball. You can see that the tennis ball shifts its position. It will move towards the side. Okay, that is, the tennis ball will start moving. First it will go this side, then to this side, then to this side, then to this side, and finally this ball come to rest. Okay, at the same time when the ball come to rest, you can see that the tuning fork would have stopped the vibrations. Okay, and come to rest. That is, the sound will be heard until when? Till the ball come to rest or the tuning fork comes to rest or it stops vibrating. Okay, so this vibrating object, even though it doesn't touch the tennis ball, it is producing the vibration in the surrounding medium, and this surrounding medium vibration is producing vibration in the board. Okay, so understood the third experiment. Here the source of sound is the tuning fork. Tuning fork is producing the sound. Okay, and we are the receiver. The sound waves are traveling through air. Air is a medium. Experiment number 4, vibrating drum produces sound. So, people who have used a drum knows that it is because of vibration. Here there is a membrane, the vibrations in the membrane that is producing sound. Now, I have a small pen stand, okay, which is made up of a metal, and I have a pen in my hand. So, here when I hit this, what happens? I am able to hear the sound and I can feel the vibration, that is, on hitting with my hands I can feel the vibration. Okay. So here what happens? There is a stick. With this stick, the drum, on the drum we will be beating. On hitting, what will happen? It will produce vibrations in the membrane. The vibrations in membrane will produce vibration in the surrounding air, and we are able to hear because vibrations are produced. That is, eardrum starts vibrating and we are able to hear the sound. So, because of the vibration in the membrane, sound is being produced by the drum. Okay. If you touch the drum somewhere, you will be able to feel that vibrations. Now, I have shown you the pen stand which is made up of a steel, or you take a steel glass or a steel plate. Okay. Take a spoon and hit it with that spoon. What happens? You will be able to hear sound. You can try this. Okay. With the spoon, when you hit it harder, you will be able to hear a different sound. When you are hitting it lighter, you will hear different sound. On different object like plate, glass, okay, you take different object, another steel spoon. All this when you take, you will be hearing different sounds in different instances and the way you hit it. Okay, so only because of these vibrations that are being produced in different objects, we are able to hear the sound. Now, in the case of a sitar, guitar, or a violin, what is happening? This string starts vibrating. Have you played a sitar or a guitar? You will see that you will be plucking the strings and sound is being heard because the strings are vibrating. Now, in the case of a whistle, what is happening? So, when you blow with a whistle, the air inside the whistle, okay, it starts vibrating and producing sound. In all these cases, we have discussed many experiments which you can try on your own. In all these experiments, we have seen that a vibrating body is a source of sound. Okay, vibrating body produces sound, which means vibrating body is a source of sound. Okay, and you can see that in all these cases, in most of these cases, air is a medium. Air is a medium through which the sound is traveling. And the third thing, there is a receiver. Let us say a human, or we are all the receivers. So, there is a sound, there is a source which is the vibrating body. Then there is a medium through which it travels, which is air, and there is a receiver which is a human. Okay. Mechanical energy is required to start vibration in a body producing sound. So, here when you take the case of a drum, with the stick you will be hitting, that is what is mechanical energy. Mechanical energy, for example, when I clap my hands, okay, I am moving my hands. So this is a mechanical energy. Okay, kinetic energy and potential energy are the two different types of mechanical energy. When I am walking, there is an energy. This is mechanical energy. When I hit this drum, okay, this energy is mechanical energy. So mechanical energy is required. We have said that sound is a form of energy and mechanical energy is helping to produce sound. We know that energy conservation, energy can neither be created nor be destroyed, it can only be transformed from one form to another. So here mechanical energy is getting converted into sound energy. Okay. So all these cases we are doing work, which means there is a mechanical energy which is applied on the vibrating body. The body starts vibrating, it is producing waves. Okay, these vibrations travel through air in the form of waves. Okay, these waves travel through the air and it reaches a person's eardrum. It starts vibrating because of the waves. Okay, vibrating waves. What happens? The eardrum starts vibrating and it produces a sensation of hearing. When you take the case of a tuning fork, hitting the tuning fork with the hammer. Okay, I am doing work, I should do a work. Okay, which means the mechanical energy is applied. Okay, here the mechanical energy is applied, sound is being produced, mechanical energy is getting converted into sound energy. This sound energy, okay, there will be vibration produced in the air. These vibrations will travel through air as waves. It finally reaches a person's eardrum. The eardrum starts vibrating and there is a sensation of hearing produced. He will be able to hear the sound. Clear? Sound propagation requires a material medium. We will be discussing a very important experiment, bell jar experiment. Okay, a material medium is necessary for the propagation of sound from one place to another. So here in the setup you can see this is a bell jar. Okay, there is an electric bell. This is airtight with a cork. It is being closed properly so that the air does not escape out. Okay, you can see the electric bell. There is a hammer of the electric bell. Okay, there is an electric circuit connection. In the electric circuit, you know, there will be a battery. There will be a key with wires, it will be connected to the electric bell. Okay. Now what happens is, initially this is the setup, that is air is present in the jar. Inside the jar there is air. Okay. So when the circuit is completing means we are giving the key. Okay, the key, or if there is a switch, the switch is pressed tightly. So we know that when a switch is on, you will be able to light a lamp, you will be able to light a bulb, you will be able to on a fan. So here what is happening, when you on the switch, the circuit is getting complete. When you off the switch, the circuit is open. There is an open circuit. When you close it, it becomes a closed circuit. So in a closed circuit, the electric current flows. Okay. So when you press the key, tightly, what happens? It becomes a closed circuit. Okay. It becomes a closed circuit. When the circuit is closed, through the wire, electric current, due to the flow of electrons, we know electrons flow in one direction when the circuit is complete, and in the opposite direction is the flow of current. Electric current starts flowing. So when the electric current starts flowing, what happens is the hammer will strike the bell. Okay, hammer will strike the bell and you are able to hear the sound. So here what happens is, when it strikes the bell, it starts producing vibrations in the bell. Okay, it starts producing vibrations. This vibrations is transmitted to the air. Okay, the surrounding air will start vibrating. Okay, so here then there is a wall of the jar. These vibrations go hit the walls of the jar. Okay, now the walls of the jar starts vibrating. Okay, these vibrations will now produce vibration in the surrounding air. Okay, surrounding air will start vibrating. These waves then travel through air and reaches our ears. Eardrum starts vibrating and we are able to hear the sound. Okay. Now here you can see the second case. Now this setup is connected to a vacuum pump. Okay. This is a vacuum pump. Through the vacuum pump, what can be done is you can remove the air outside. Okay. So gradually here the key is kept pressed. That is, the electric current is flowing through the vacuum pump. Now what happens is air is started to remove. We are removing the air slowly. Gradually air is removed. What happens is, we know that the sound needs a material medium to travel. Air is a medium here. When you start removing the air, what happens is slowly the sound heard, okay, its intensity decreases. That is, loudness decreases. It starts decreasing. Okay. Why? Because air inside is decreasing. Okay. Air inside is decreasing, therefore the vibrations produced will decrease. The vibration produced in the wall of the jar will decrease. In the surrounding air, the vibration produced will be decreasing, which means the vibrations that is produced in the eardrum is decreasing and the sensation of hearing is decreasing. We won't be able to hear the sound that was heard before. The loudness has decreased. Okay. Now the third case is there is no more air left inside. Then what happens? Okay. Completely through the vacuum pump, you are removing all the air. So, the sound can travel through a solid, it can travel through a liquid, it can travel through a gas, but it cannot travel through vacuum. There should be any one medium for the sound to travel. So, even though you will be able to see that this hammer will be hitting the gong, okay, it will be vibrating, but you won't be able to hear any sound. The circuit is complete, key is pressed properly, okay, the electricity is flowing through the wire, the hammer is hitting the bell, it is hitting the gong, it is vibrating, but still you won't be able to hear the sound, because even though vibration is producing here, these vibration cannot reach the walls of the jar. Why? Because there is no medium for its travelling. Okay, because it is not travelling, what happens? You won't be able to hear any sound. Okay, no sound is heard. Understood? So, this experiment is a very important experiment and it explains very clearly that sound requires a material medium to travel. Without a material medium, sound cannot travel. This is a bell jar experiment. Okay, electric bell inside a jar. Requisites of the medium. We said that there should be a material medium for sound to travel. It can be air, it can be glass, it can be water, it can be any solids, okay, but it requires this material medium. There are some requisites of the material medium, okay. The medium required for propagation of sound must possess the following three properties. First one is the medium must be elastic. So, when you take the case of a rubber string, okay, first experiment, what you did, you took the rubber string, it was held, one end was held inside your mouth, with your teeth you are holding it tight, other end your hand or holding it in your hand, okay, you pluck the rubber string and it starts vibrating. So, it is an elastic body, that is vibrations. Elastic body means these vibrations are produced, which means it is moving down, it is moving up, moving down, moving up, moving down, moving up. So, when you just pluck it, okay, when you take a plastic, okay, so when you try to do the same thing with a plastic, what happens then? It will break. You cannot apply more force, it will finally break. Okay, so to produce sound, to produce vibration, you need an elastic medium. Second is the medium must have an inertia. What is inertia? Inertia is a body's ability to remain in a state of rest or uniform motion. Okay, so here when you just produce, you just pluck it, it is able to remain in a state of motion for some time. Yes, so this body should possess, the body that we are using to produce vibration must have an inertia. Now third, the medium should be frictionless. What happens if there is friction? Due to friction there will be loss of energy. Okay, to prevent this you will have to choose a medium which is frictionless. So these are the requisites of the medium. When you choose a medium, the medium, it should be elastic, then it should have its own inertia and it should be frictionless. So we have said that sound needs a medium to travel, it cannot travel in vacuum. So bell jar experiment is a very good experiment which explains that the sound can travel only through a medium. So here we have said sound can travel through air, it can travel through, that means it can travel through gas, it can travel through liquid, it can travel through solid. Okay, we will discuss some experiments. So here you can see a toy telephone, or when you were in smaller classes you might have tried this, that is on your bench, your friend will be lying on the bench, okay, he will keep his ears on the bench and he will be lying. So what, he will be in deep sleep, then what you do is you will start hitting the bench with your hands. What happens? He will suddenly wake up. Why? Because what is happening when you hit the bench, okay, when you are hitting on the bench from the other side, what happens is the particles in the bench, it will start vibrating, okay, this vibration will travel through it, okay, all the particles on the bench will start vibrating and finally reach the person on the other side, it will reach his ears. His eardrum will start vibrating and the sensation of hearing is produced. So you can see a toy telephone, you can see that there is a cup, a thread, another cup, okay, two matchsticks are there, okay. So here you can see one person is speaking and other person is hearing. So what is happening? Through this cup, okay, through this thread, the sound waves are travelling. Sound is a form of energy and the sound is traveling through the wire and the other person is able to hear it. Okay, so this is a toy telephone. Now, sound can travel through a liquid. So, here you can see the boy, he has taken water, okay, and a bell is completely immersed inside the water. He is trying to ring the bell, okay, ring the bell, that is, it is vibrating, the bell, gong of the bell is vibrating and he is keeping his ears over the surface of water. He is able to hear the sound. Why? What is happening here? In this case also, the sensation of hearing is produced because vibrations are produced inside the water. Okay, this vibration will reach the person's ears, eardrum will start vibrating and the person is able to hear the sound. Now, when you take the case of gases, I am speaking from here, which means I am producing vibration. These vibrations are traveling through air. Air is a gas, okay, it is a medium. It is traveling through gas. Then what happens? Vibrations are produced, waves are produced, it will be reaching your ears and you are able to hear because the eardrum vibrates. When you go to moon, okay, do you know this thing? On moon, is there air? Is there atmosphere? No, right? There is no air, there is no atmosphere on the surface of moon, which means there is vacuum. Okay, then what happens? If you and your friend is traveling through moon, okay, you went to moon and you want to speak to the other person. Can you speak? You can speak, but the thing is that he won't be able to hear. What is the reason? He won't hear you because there is no medium for the traveling of sound waves that you are producing. You are producing sound, you are the source and there is a receiver, but the receiver is not able to receive the sound. Why? Because three things are important. There should be a source, there should be a receiver, there should be a medium. Here source is there, receiver is there, but there is no medium. Only if there is medium, the sound waves can travel. Since on the surface of moon there is no medium, there is no air, the sound cannot travel and it cannot reach the receiver. So if you are asked, can you speak to your friend when both of you are on the surface of moon? It is not possible. Speaking is possible, the person won't be hearing you. Okay, mechanical waves. There are two types of mechanical waves. One is longitudinal waves and the second one is transverse waves. So, what are longitudinal waves? Example for longitudinal waves. So, we have discussed an experiment with tuning fork. So, when you take a tuning fork and hit it, waves are produced. These waves are called longitudinal waves. With the experiment, we will understand them in detail. A simple example for longitudinal waves is the waves that are produced in case of a tuning fork. Okay, next, transverse wave. There are many examples for transverse waves in our daily life. When you take a rubber band, the first experiment that we have done, take a rubber band, hold it one hand with your hands, with your fingers, one end with your fingers and the other end inside your mouth, you make it vibrate, you pluck it, you make it vibrate. You can see the waves are produced. These waves are called transverse waves. Another example is guitar string. Okay, you are plucking the guitar strings, vibrations are produced in the string. This is also an example of transverse wave. Next example, you put a stone inside a water body, like we can say inside a well or a pond. You can see ripples. Okay, these types of ripples will be produced. This type of ripples will be produced. This is an example of a transverse wave. So, many examples are there for transverse wave. Oscillating, then you take a rope. Okay, you take your rope, you hold your one hand with the rope and the other hand your friend holds and you starts to vibrate it. Okay, that is, you will be able to see this type of waves. So, this is also an example of transverse waves. So, understood what are longitudinal waves and transverse waves? You got the examples. So, we will discuss them in detail with experiments. First, we will discuss about longitudinal wave. We have given an example. Example of longitudinal wave is a vibrating tuning fork. So, we will discuss an experiment. Take a metal strip. Okay, a metal strip is taken. One end, it is kept in a vertical position. One end of it is fixed. Okay, it is fixed somewhere. Okay, and the other end is made to vibrate. For example, you take a blade, hold one side with your hands and the other end is made to vibrate. Similarly, here one end is fixed and the other end is made to vibrate. Vibrate means you are pulling it to one side and then releasing it. Okay, so here you can see there is air. Okay, so when you pull it to one side, what happens? You will be able to see that first it will move to this side, then it moves to this side, again this side, this side, this side, this side, right, left, right, left, and then finally come to rest. Okay, so first it is moving to the right. You are able to see it is moving to right. Then what happens is when it moves to the right, the surrounding air, okay, air which is on this side, what happens is it will start coming closer. That is, these particles are pushed to one side. Okay, it goes closer, it comes closer. Okay, so a region is produced where the particles are very close to each other. Okay, very close to each other. So when you take the case of a spring, okay, if you have a spring, you are first expanding it, okay, or you are first contracting it. What happens? The strings, the wires, particles, it comes very closer when you compress it. Okay, this is called a compression. Okay, that is, the particles of air are coming closer to each other when it is pushed to one side. Okay, so this we call the compression. Compression. Then what happens after compression? This metal strip which moves to one side will then reach the maximum distance. Okay, this end will reach the maximum distance and then come back to its original position and move to the other end. Okay, other extreme end it will be moving. So here what happens is the air particles which was compressed now gets released. Okay, it gets relaxed. So the particles in this region, the particles will be apart each other. Okay, there will be more spaces between the particles. So this region we call the rarefaction. So understood what is compression and rarefaction. So when the metal strip it moves to one side, to the right side, what happens? The particles of air are coming close to each other. It produces a compression. Okay. Then when the metal strip moves to other side, the particles of the air are released. It is relaxed. Okay. This region we call the rarefaction. So one compression and a rarefaction. That is, here it starts, move to one side. Okay, come to its original position, move to the other side, come to its original position. So here a compression is produced, a rarefaction is produced. This compression and rarefaction together, okay, one compression and one rarefaction together we call a wave. So this constitutes a wave. Okay, so in case of compression, first case, when in case of compression, the density and the pressure will be higher. Density higher is when all the particles are closer to each other. We know density is mass by volume. Density is equal to mass by volume. So when the particles come close to each other, what is happening? Volume is decreasing. Volume is inversely proportional to density, which means the density will be increasing. Okay, so there is maximum density and maximum pressure at the region of compression. Maximum density and maximum pressure. Okay, now in the region of rarefaction, there is minimum density and minimum pressure. In all other regions, between the most compressed state and the more rarefaction state, all other regions, the density and the pressure will be in between. Okay, in between that of compression and rarefaction. Understood? So this is what a longitudinal wave is. We can see the to and fro motion. If the vibration of medium particles are along the direction of propagation of the waves. So here you can see this is the direction in which the particles are vibrating. In the same direction is the direction in which the waves are moving. Okay, they are parallel to each other, forming compressions and rarefactions are produced in the medium. The wave is called a longitudinal waves. In case of longitudinal waves, the particles are vibrating in the same direction in which the wave is propagating. Okay, this is a longitudinal waves, and just remember one example for a longitudinal wave. Next one is transverse wave. We have discussed in detail about longitudinal waves with an experiment. So we have seen that in the case of longitudinal waves, we are not able to see the waves. Okay, what we are able to see, we cannot see how the wave travels in air. What we can see, the only thing that we can see is that we can only hear the sound. Okay, but we are not able to see. Now when you take the case of transverse wave, we will discuss an experiment here also. So here we are considering water on a surface of pond. Okay, water which is on the surface water we are considering. When you drop a stone, all of you might have tried this before, or you can now also try this, okay. When you take a stone and drop it into the water in a pond, okay, surface water in a pond, what happens? So if this is the surface of water, you are dropping a stone, okay, you will be able to hear a sound and you will be able to see ripples on the surface of water. These type of ripples will be produced, okay. Now if you take a cork, okay, or a piece of paper and place it somewhere over here, you will be able to see that it will be moving up and down. In which direction is wave moving? Wave direction is this way, and you place a particle on it, in which direction it is moving? It is moving up and down. That is, it is not actually getting displaced, but till it comes to rest, till the disturbance gets closed, you will be able to see that it is moving up and down. That is perpendicular, okay. So if the medium particles vibrate normal means perpendicular to the direction of propagation of the wave, forming crust and troughs, the wave is called a transverse wave. So we have discussed other examples of transverse wave as well. So what are the examples? The string, the waves that is produced in the case of strings of a guitar, okay, or when you take the rubber band experiment, okay. In all these cases you are able to see there is an up and down motion. Okay, this is the direction in which the wave is traveling, and the motion of the particles is up and down, perpendicular to the direction of propagation of the wave. Okay, so these types of waves we called, if the particles of the medium are vibrating perpendicular to the direction of motion of the wave, we call it as a transverse wave. In case of transverse wave, the maximum displacement to the upward displacement, and there will be downward maximum displacement. This upward maximum displaced position that we call the crust. Okay, so this is a crust, and this one we call a trough. Okay, so we start from a crust, you reach a trough, then you reach a crust. Okay, this from here to here, the total distance, there will be a total distance. This constitutes a, okay, this one we call it as a wavelength. Okay, here starting from one point, okay, I am starting from here to here to here, okay. This is a complete wave. Or from one crust, if I am starting from this crust through trough to the other crust, this is a complete wave. Okay, from crust to the other crust, the consequent crust, it is a wave. Okay, or from a trough to the other trough, it is a wave. Okay, so a compression and rarefaction together constitute what? It constitutes a wave in the case of longitudinal waves. Now, in case of a transverse wave, okay, an upward motion and a downward motion to the initial position when it reaches, it constitutes a wave. Or from a crust to the other crust, it is a wave. From a trough to the other trough, it is a wave. Got it? So this is all about transverse waves. So when you are discussing about waves, there are some important terms that you need to keep in mind. So first one is amplitude. So this is how you represent a wave. Okay, you know what is a crust, what is a trough. The maximum upward displacement and the maximum downward displacement are called crust and trough. Okay, we know what is a wave also. So here first term that we are going to discuss is amplitude. Okay, what is amplitude? Amplitude is the maximum displacement. So here this is the mean position. Okay, when you take a rubber string, you are holding it tightly. Okay, which means it is at a mean position. It is at its mean position. Particles are in mean position. Now when you plug, what happens? The position is changing. It goes to the extreme end, then comes back to the upward extreme end. This happens. Okay, so here the maximum displacement we call the amplitude. From here, this is the mean position, to its maximum height, this makes an amplitude. Or from here to here, this maximum distance we call the amplitude, which is represented by small letter A. Okay, the maximum displacement of a particle of the medium on either side of its mean position. Either side, upward direction is one side and downward direction is the other side. If you are considering the longitudinal waves also, there will be amplitude. Okay, this we call the amplitude, represented by letter A, and the unit is meters. Normally lengths we measure. SI unit of length is meter, amplitude is a length, therefore the unit is SI unit is meters. Next is the time period. Okay, so the time taken by the particle of the medium to complete its one vibration. So what is one vibration? In case of longitudinal wave, one compression and one rarefaction together constitute a vibration. To and fro motion, alright, an up and down motion completes a vibration. So if I am starting from here, moving down, moving up, okay, one crust and one trough is included. Okay, this is a complete vibration. Okay, now what is time period? The time taken by the particle to complete one vibration. So in what time is one vibration completed? This we call the time period, represented by the capital letter T. What is the unit? SI unit will be seconds, represented as S. Next is frequency. Frequency and time period are related. Okay, so we have said that time period is a time taken. Okay, so time taken to complete one vibration. And about frequency, when you discuss the number of vibrations made by the particle of the medium in 1 second. Here the time is 1 second. Okay, time is 1 second. In 1 second, the number of vibration possible in this 1 second we call the frequency, which is represented by small letter f. And the relation between frequency and time period is frequency is inversely proportional to time period. Frequency is equal to 1 by time period. So when time period increases, what happens to frequency? Frequency decreases. So what is frequency? Frequency is the number of vibrations in 1 second. The time here is 1 second. How many vibrations are possible in 1 second is called the frequency. Now frequency is represented either by the small letter f or small letter n or a Greek letter. This is how you represent it. It is called nu. Okay, Greek letter nu can be used to represent frequency. Now the SI unit is, we have said frequency is equal to 1 by time period. Okay, unit of time period is seconds. So 1 by seconds or second inverse. Second inverse is one unit of frequency. The other unit is hertz. Hertz is the SI unit of frequency, represented by Hz. Hz is frequency. Okay, so the frequency depends on the medium. Okay, it depends on the source. So here the source will be producing vibrations. So that body which is producing vibration will show how much frequency it has. So frequency is completely dependent on the source. Next is wavelength. Okay, wavelength is represented by the letter lambda. So we have discussed it before. So what is wavelength? The distance from one crust to the consecutive crust is called the wavelength, or from one trough to the consecutive trough we call the wavelength. The distance travelled by a wave in one time period, or you can define it as the distance travelled by a wave in one time period of vibration of the particle of the medium is called the wavelength. So what is time period? It is a time taken by the particle of the medium to complete one vibration. So one vibration means from here to here, or from here to here, or from here to here. This is one vibration. So we can say that wavelength is the distance it travelled. Okay, it is the distance travelled by a wave in one time period. In one time period, how much distance it travelled. It is represented by a Greek letter lambda. Okay, this is how lambda is represented. Normally, the wavelength unit, SI unit is meter, because it is also a length. Other commonly used units of wavelength are nanometers. That is, 1 nanometer will be equal to 10 raised to minus 9 meters, or 1 angstrom. Angstrom is another unit which is 10 raised to minus 10 meters. Okay. Now the next one is wave velocity. Wave velocity is the distance travelled by the wave in 1 second. Okay. So distance travelled by a wave in one time period is called wavelength, and the distance travelled by the wave in 1 second is called the wave velocity. Okay, what is the unit of wave velocity? What is the unit of velocity? We know the unit of velocity is meter per second. Therefore, the unit of wave velocity will also be meter per second. Okay, so these are the very important terms that you have to remember when you discuss about a wave. Amplitude, time period, frequency, wavelength, and the wave velocity. Now we will be discussing two important graphs. First is the displacement time graph. In a displacement time graph, it shows a variation of displacement with time for a particle of the medium at a given position when a wave propagates through the medium is called the displacement time graph. So here we know that when a body vibrates, vibrations are produced in the surrounding medium. That is, the particles of the medium are getting vibrated. Okay, it gets vibrated, it moves to one position, come back to its mean position, moves to another position, come back to its mean position. With time, how is the displacement of this particle? First, initially, first particle vibrate, it is transferred, the vibration is transferred to the next particle, the second particle vibrate. This is happening continuously. So in case of a displacement time graph, the time is taken along the x-axis. The unit of time is second. And then vibrations, okay, here we will be taking displacements along the y-axis. Displacement in meter is taken along the y-axis. Okay. Now, when you consider a wave, this is how a wave is: upward motion, downward motion, upward motion, downward motion. The maximum displacement we call the amplitude. The maximum displacement from the mean position is the amplitude. So this is amplitude. Okay. Here x-axis displacement. Then you have time period. So what is time period? To complete a vibration, the time taken we call the time period. Okay. So what is one vibration? From the mean position, upward motion, downward motion, back to mean position. So this is a complete vibration. Or starting from a crest, then to trough, then to crest. So this is a vibration. Okay. For this, the time taken we call the time period. Or from a trough to the next trough, the time is the time period. So here this is time period, or this is time period, because time is now taken along the x-axis and displacement is along the y-axis. So here we are able to represent the amplitude and the time period on the graph. Okay, on the curve we are able to plot it. Next is the displacement distance graph. In a displacement distance graph, displacement as usual is taken along the y-axis. Displacement along y-axis, and distance is now taken along the x-axis. In the previous graph, time was taken along the x-axis. Here distance is taken along the x-axis. Usually we have a wave represented in this way. So this is a wave. Okay. Maximum displacement is the amplitude. So displacement A we are representing here. Now on this graph, okay, x-axis shows the distance, okay, from a crest to the next crest, or from a trough to the next trough, or from the starting of the wave back to its mean position after the upward and downward motion, we get a complete vibration. Okay, this complete vibration makes the length when measured, you will be getting the wavelength. So this is a wavelength lambda. The wavelength lambda. Okay, the curve showing the displaced position of particles of medium from their mean positions at an instant when wave propagates through the medium. So here we have taken the case of a transverse wave. Okay, so this is what a displacement distance graph. The plot is the same. Here we will be representing amplitude and wavelength, because wavelength is the distance and amplitude shows the displacement. Okay. In the previous graph, we have taken the time period and amplitude, because amplitude is the displacement is represented by amplitude and the time taken is represented by the time period. Okay. The relationship between wavelength, wave velocity and frequency. So consider a wave whose wave velocity is capital B, time period is capital T, frequency is F, and wavelength is lambda. Okay. So what is wavelength? We know what is the definition of wavelength. Wavelength is the distance travelled by a wave in a one time period or in t seconds. Okay, we know that speed is equal to distance by time. Okay, which means distance will be equal to speed into time. So here the distance is wavelength. Okay. Time is the time period. And what is the speed? Speed is the wave velocity. So we will be having wavelength lambda is equal to wave velocity into time period. Okay, that is equal to lambda, which means lambda is equal to capital V into time period T. Okay. We have a relation between time period and frequency. What is the relation? Frequency is equal to 1 by time period, inversely proportional, or F is equal to 1 by T. Okay. So in place of T, what can we write? T will be equal to 1 by F. Okay. So lambda is equal to V into 1 by F. Okay. If lambda is equal to V into 1 by F, okay, then what is V? V will be equal to lambda into F, which means wave velocity is equal to wavelength into frequency. Wavelength into frequency is the wave velocity. So this is the relationship between wave velocity, wavelength and frequency. If you want in terms of time period, then what you will be having? Wave velocity V is equal to lambda divided by T. Wave velocity is wavelength divided by time period. Okay. Got the relationship? So you can use this relationship. If two quantities are given, we can find the third quantity. For example, time period and the wavelength is given, you can find wave velocity. If wave velocity and wavelength is given, you can find the frequency. If frequency and wavelength is given, you can find wave velocity. If wave velocity and frequency is given, we can find the wavelength. Okay. Unknown quantity can be determined. Speed of sound in different medium. Okay, so when you take the case of a blacksmith with his hammer, he is hitting an iron piece. Okay, so he will be hitting and you will be hearing the sound. There will be a time interval between the hitting of the iron piece and you hearing the sound. Okay, there is a small time gap. So this small time gap is because of the speed of sound. Okay, what happens is when he hits the iron piece with the hammer, vibrations are produced. This vibrations should travel through the medium, which is the air. Okay, so while traveling through air, what is happening? There is a speed of the sound, and the speed of the sound, it depends on the medium. Okay, in medium in which it is traveling. So it depends on two factors. One is the elasticity of the medium and second is the density. Now when you take the case of a cracker, you are bursting a cracker. After you burst, once it starts catching fire and the sound is heard. Yes, so there will be a time gap between it bursting and you hearing the sound. So why is it happening? Because the sound waves has a speed and this travel through a medium. So it depends on the medium's elasticity and the density of the medium, and the relation is speed of sound V is equal to root of elasticity divided by density of the medium. So this is a relation. Okay, this is how the speed of sound, it depends on elasticity and the density of the medium. So speed of sound is directly proportional to the root of elasticity. Speed of sound is inversely proportional to the root of density. So when density increases, what happens? Speed of sound decreases. Okay. When the elasticity increases, what happens? The speed of sound also increases. They are directly proportional. Other case, it is inversely proportional. Now we have an equation, that is the speed of sound. It depends upon the elasticity of the medium, modulus of elasticity and density of the medium. Okay. So Newton first assumed that when a sound wave travels through a medium, there is no change in temperature. Okay. There is no temperature change. Yes, so in this case, the modulus of elasticity will be equal to the pressure. Elasticity will be equal to pressure, which means we can write the equation speed of sound is equal to pressure divided by the density. Okay, if you know the density and you know the pressure, okay, then you can find the speed of sound at normal temperature and pressure represented by NTP. The pressure value is equal to 1.01 into 10 raised to 5 Newton per meter square, and density is equal to 1.293 kilogram per meter cube. So using these values, when you calculate V, root of pressure, that is 1.01 into 10 raised to 5 divided by 1.293, when you divide it, okay, and take the square root, you will be getting V value approximately equal to 279.5 meter per second. Okay, so this is a calculated value with the considering the normal temperature and pressure. Pressure value is taken and density of the medium, that is air, is also taken, and this is calculated. You are getting some value which is this one. So experimentally, when the value of the velocity or the speed of sound was taken, the speed of sound V is equal to 330 meter per second. So what do you understand from this? The value, the calculated value is less than the experimental value. Yes, there is a difference in the speed of sound. Yes, there is a difference. So what should be done? At normal temperature and pressure, when the velocity, when the speed of sound is calculated, there is a difference. Okay, so what was Newton's assumption? Newton assumed that when sound travels in the gas, the temperature of gas does not change, because this is taken as an isothermal change. Isothermal change means the temperature remains the same. Okay, but we have found that when this assumption is made, the speed of sound that we are getting calculated value is less than the actual experimental speed of sound, which is 330 meter per second. There is a difference. So we have a relation, that is the speed of sound is equal to root of pressure divided by density. So here we have considered Newton's assumption, that is an isothermal change we have considered, there is no temperature difference. But later on what happens is Laplace made an assumption, that is according to Laplace, when sound travels in a gas during the formation of compression and rarefactions, compressions and rarefaction will be reduced, there is no change of heat in the medium, no change of heat. This type of process we call the adiabatic process, adiabatic change. Okay. Adiabatic change means there is no change of heat in the medium. Okay, temperature is kept aside, here heat is considered, there is no change in heat. Then the relation becomes V is equal to root of gamma P divided by rho. Now what is gamma? Gamma is a Greek letter. Here gamma will be equal to Cp by Cv. So what is Cp? What is Cv? Cp is a specific heat at constant pressure. Specific heat of a substance at constant pressure, and Cv is the specific heat at a constant volume. Then you get rho. Okay. Then you get gamma. Gamma multiplied with P, pressure, divided by the density rho. Taking the root, you will be getting a value for the speed of sound, V. Okay. So when you calculate, considering you are including this rho, you are including this gamma as well. In that case, you will be getting a V value. Here V value will be equal to 330.7 meter per second. Approximately equal to the experimental value. So here for air, the gamma value will be equal to 1.4. So how is the calculation? We have pressure is equal to 1.01 into 10 raised to 5 Newton per meter square, and density rho is equal to 1.293 kilogram per meter cube. Substituting, we get V is equal to root of 1.4 into 1.01 into 10 raised to 5 divided by 1.293. So this value is equal to 330.7 meter per second. Approximately this calculated value is equal to the experimental value, which is 330 meter per second. Okay, so when you consider solids, liquids, gas, in different mediums, the speed of sound is also different. In solids, the speed is maximum. In liquid, it is lesser than that of solids and greater than that of the gases, and the minimum is in the case of gases. So if you are asked, when you clap your hands and your friend who is at a distance of say 2 meters, okay, hearing a sound, and you tap on a desk with the same energy you are tapping on a desk, and your friend is hearing who is at a distance of 2 meters at the other end of the desk, keeping his ears on the desk. Okay, in these both cases consider in which case does the person hear the sound more sound, it will be, or faster the sound will be heard when the sound waves travels through the solid, it travels through the desk. Why? Because speed of sound in case of solids is higher compared to the speed of sound in gases. Okay, so this correction is also included and you get this formula to find the speed of sound. Now let us solve questions from exercise 8a. Question 1 of exercise 8a. The heart of a man beats 75 times a minute. What is its frequency and time period? So here it is given that a person's heart beats 75 times a minute. We know that frequency is the number of vibrations in 1 second. So here it is given in 1 minute 75 times, which means in 60 seconds, 1 minute is equal to 60 seconds. In 60 seconds 75 times, or in 1 second it is equal to 75 divided by 60 times. Okay, what is 75 by 60? 15 into 5 is 75 and 15 into 4 is 60. So 5 by 4 equal to 1.25. So therefore we can say frequency is equal to 1.25 Hertz. Okay, Hertz is a unit of frequency. Now we have to find the time period. There is a relation between time period and frequency. Time period is equal to 1 by frequency. So here time period is T equal to 1 by F. T is equal to frequency is 1.25. Okay, or we have F is equal to 5 by 4, which means 1 by F will be equal to 4 by 5. Therefore time period is equal to 4 by 5, which is 0.8 seconds. So we have got the time period and frequency of the heart of a man which beats 75 times a minute. Next, question number 4 of exercise 8a. A longitudinal wave travels at a speed of 0.3 meter per second and the frequency of the wave is 20 Hertz. Find the separation between the two consecutive compression. The separation between two consecutive compression or the separation between two consecutive rarefaction is same as the separation between the distance between two consecutive crust or two consecutive trough, which means this is a wavelength. So here we are asked to find the wavelength lambda. Wavelength lambda. So what is given? The speed is given, speed v is equal to 0.3 meter per second. Then frequency f is given, which is 20 Hertz. Okay. Now we can find the wavelength. What is the relation? We have speed is equal to frequency into wavelength, which means the wavelength will be equal to speed divided by frequency. Here the speed is 0.3 divided by frequency is 20. Okay. So this can be written as I am multiplying with 100 on the numerator and denominator. So this becomes 30 by 20 into 1 by 100. Equal to, what is 30 by 20? 3 by 2. 3 by 2 is 1.5. So 1.5 into 10 raised to minus 2. When this goes to the numerator, this is 10 raised to 2. When it goes to the numerator, it becomes 10 raised to minus 2. And the unit is meter. Okay. So 1.5 into 10 raised to minus 2 meter is the wavelength. Okay. That is the separation between the two consecutive compression. Separation between two consecutive compressions is 1.5 into 10 raised to minus 2 meters. Okay. Question 8 of exercise 8a. A boy fires a gun, another boy at a distance hears the sound of fire 2.5 seconds after seeing the flash. If the speed of sound in air is 340 meter per second, find the distance between the boys. We have to find the distance between the boys. Okay, A, B are two boys. We don't know what the distance is. Distance is D. Okay, so A is firing a gun and B is able to hear the sound in 2.5 seconds, which means time taken. T is equal to 2.5 seconds. Also, what is given? The speed of sound is given. Speed V is equal to 340 meter per second. When we know speed and time, there is a relation. We have speed is equal to distance by time. If speed is equal to distance by time, then what is the distance? Distance will be equal to speed into time. Okay, so here the speed is 340 and time is 2.5, which is equal to 340 into 25 divided by 10. Okay, or again multiplying with 10, here it becomes 100, cancelling this becomes 4. So 340 divided by 4. What is 340 divided by 4? In 34, we get 8, 20 remaining, 20 by 4 is 5. Again a 0 is there. So 850 meter. So distance between the two boys is equal to 850 meters. Next question 10 of exercise 8A. How long will sound take to travel in A, an iron rail, and B, air, both 3.3 km in length? Take speed of sound in air to be 330 meter per second and in iron to be 5280 meter per second. Okay, so what is given? We are given the distance is equal to 3.3 kilometer, which is 3300 meters. Okay, so first we will find in case of an iron rail. In case of iron rail, the speed is given V is equal to 5280 meter per second. Distance is the same, D is equal to 3300 meters. Distance we know, speed we know. Then what is the time? T is equal to distance by speed, which is 3300 divided by 5280. You cancel, when you find, you will be getting 0.625 seconds. Okay. Next, in case of air, we are going to find speed is equal to, in case of air it is 330 meter per second. Distance is equal to 3300 meter. Okay. Then time will be equal to distance by speed, which is 10 seconds. Okay, 10 seconds is the time. Clear? So we can see that 10 seconds is the time taken in air and just 0.625 is the time, seconds is the time taken in case of iron rail, which is greater. More time is taken in the case of air, which means the speed is greater in the case of iron rail, which is a solid. That's all for today. In today's class, we have discussed the production and propagation of sound wave. We have also solved questions from exercise 8A. Hope you all enjoyed this session. I'll be back in the next session. Until then, stay tuned to Learnohub. Learnohub free hai, par best hai. Thank you.